How many parts does it have, Iyad?
3.
Oh, it's a long section A question though. And which part are you on?
1.
Okay. Here's Mayor. Right? No, that wasn't him that way. He walks slow.
How could you hear someone?
I could hear the door just like further down the hall. Alright, which part now, Iyad?
2.
Do you feel like you got one?
No.
Then maybe I should just do it?
Yeah.
Okay, fine, fair enough. Right, so give me the info. What's the story?
Square.
Yeah.
A square coil of wire of area 25 centimeters square is mounted
Yeah.
so that it can rotate about the vertical axis, which is at right angle to a uniform magnetic field of 750 milliliters.
Okay, let me just draw that so far. So there's your square, 25 meters squared, and it rotates like this, and there's a magnetic field here and here. I suppose you said it's mounted vertically.
Yeah, mounted so that it can rotate about the vertical axis.
A vertical axis? Why do they do it like that? So then it's, okay, whatever. 25 centimeters squared, and then it's rotating around a vertical axis, okay, and then there's a magnetic field as well of 750 millitesla. Okay, what's next then?
Determine the magnitude of the force acting on each vertical side of the coil if it has 100 turns of wire and the current of 800 milliamperes is known.
Okay. I'm not going to draw it vertically, that just looks silly. It doesn't really matter. So it's spinning this way, it has a north, it has a south. The magnetic field is going from north to south. That's 750 millitesla. This is 25 centimeters squared. And the current in the wire is, what did you say? How many amps? 800 milliamps. Okay. And the question is, what is the force?
Determine the magnitude of the force.
Yeah. So this is the formula. You have a couple of formulas for this topic. You have the torque, which is I-band. So that's not the one we want here because we don't want to turn in force. And then you have force equals N bil. And that's the one that we want here. So force equals, how many turns did you say? 100 turns.
Yes.
So that's 100, 0.75, 0.8. And the wire's length is 20 centimeters. Now, why is it 20 centimeters? Thank you. We had the charger all along. Isn't that funny?
Because it's square.
Yeah, go on.
We have the area square.
Yeah.
So
it must be a 5 by 5 square. Because it's 25. So that's 5, 10, 15, 20. Yeah? Yeah?
Yes.
So just bash this in on the calculator and what do you get? Which year is this from here?
12, 14. Sorry, 12, 13, 14.
Oh, 13, 14. Version 2. A7?
Yes.
12.
Exactly 12.
Yes.
Great. That's part 1.
That's going good, yeah?
Huh? Yeah.
We're doing the first part.
Yes.
Then 100 turns is n.
Huh?
100 turns is n.
No, the end.
Yeah.
Right, what's the next part, Adnan?
So, after you go.
Well, I've already written down the formula for torque. So, torque is I-ban.
To the plane of the coil, is that a right angle to the magnetic
That's not important for the... They want the torque.
Yes.
Yeah. So that is I, B, A. Now, we have to work out the A
You don't have any?
in meters squared.
I saw a video, like they said divided by a million, is that right? Or?
Yeah, that would do it. Divide by a million.
Million.
I said. But I'm going to work it out in size here. So 25 centimeters squared.
0.0625.
You have it there?
Yeah.
Great.
10 to the minus 2.
But like how,
Great, yeah.
how do we do it? 10 minus 2, 10 minus 4.
Hold on, I'm doing it. 25 centimeters squared. 25 centimeters squared, which is 25 10 to the minus 4 meters squared. That is 0.00025 meters squared. You squared the 25, didn't you?
No, I squared the whole thing.
You said you got a 625.
Yeah, still did.
Yeah, well, what did you square?
25 times 10. Oh, I squared the whole thing.
Yeah,
Okay.
okay, so
So 2.5 to the power of minus 5.
the final answer?
No.
Oh, okay, yeah.
We can.
1, 2, 3, 4. No, what was that? 2.5? 1, 2, 3. Well, if it's 2.5, it's the minus 4. And if it's 25, it's the minus 3. Okay, what's the answer here?
0.015.
0.015? Okay, Iyad, you can tell me the last part then when you're ready.
Determine magnetic flux linked with each turn of the coil when the perpendicular to the plane of the coil is at an angle of 60 degrees to the field direction.
Right, so this is the one NBA cos theta. They said flux.
Yeah.
Did it say flux linkage or flux?
Flux linked with each turn.
Oh, I wish they said linkage instead of linked. I think they mean linkage. The difference is flux is just for one and linkage is the total. So I'm going to go with the n in the formula. And I think it's cos theta. Let me think about this. When it's... Can you just read again, please? I want to make sure I have the right...
Determine the magnetic flux linked with each turn of the coil when the perpendicular to the plane of the coil is at an angle of 60 to the field direction.
So it's maximum at 0. Yes, okay, I think this is the correct one. Anyway, this formula is in the formula book. This is in the book anyways, if you can't remember if it's cos or sine. So the n is 100, the b is 0.75, the a is 0.00025, and that's cos 60, you said. Right, so what do we get here?
So when it's perpendicular, we use cos.
No, it's not to do with perpendicular, that's just how they measure the angle. It's always cos, and it's always, another one always has sine in it. But I sometimes forget which is which, but they're both in the formula book.
9.3 to the power minus 3. to the power minus 4. And the answer is minus 4, but I have it minus 3.
Do they have 9.38 or 93.8?
9.38.
And you have,
9.375.
but do you have the right number of zeros here?
Yes.
Let's have a look.
0.30,
Maybe my area was wrong, I don't know.
No.
It's right? Here, let's have a look. 100 times 0.75 times 0.00025 times cos 60, and you get, yeah, 9.375 milli. You must have typed in something wrong out there. Well, you must have, because I typed in the exact thing on the...
No, it's the same thing, but this one to the power minus 3, and the answer is the power minus 4.
Oh, maybe it's a typo. Or maybe I missed a zero somewhere.
I think it's right, because it's 750 multiplied 10 minus 3.
Yeah.
25 10 minus 4, cos 60.
Yeah, that's the same thing. Wait, did they have 100 at the start?
No, 100, no. 750 to the power minus 3, 25 to the power minus 4, cos 60.
So it's the plus linkage.
They don't have n.
So then, they didn't want the flux linkage, they wanted the flux.
They just BA cos theta.
Oh, well then, I shouldn't have had this, and I shouldn't have this then. So that means my answer is 100 too big. So I need to divide by 100.
They said linkage.
Yeah, I know, it seems like such a... Yeah. Okay, well I guess we have our answer then. It has to say linkage. I wonder if they did that on purpose.
The unit changes as well, doesn't it?
Oh, sorry, thank you. Yeah, it's Weber's, isn't it?
Yeah.
So what's it now? It's different, isn't it? It's don't have the 100 in it.
Yeah, it's just minus 3, minus 4.
9.375 10 to the minus 5 times 10 to the minus 5 Webers. Yeah. Or if you want, that's 93.8 micro Webers. Okay, so is that the end of the question?
Yes.
Yeah.
Okay, so it's entirely up to you now. You give me another question you want to see, and that's what I'll do.
B2 is about simple harmonic motion. Where do you want to do simple harmonic motion?
Do you want simple harmonic motion?
Yeah.
Okay.
No.
No.
Do you guys want it? Do you want it? Did you say yes? Okay, fine.
But do you know how
It's
to...
alright. I mean, we did one before. Okay, fine.
It's okay?
Yeah, I
B2.
mean, no,
Well, is it a hard simple harmonic motion one? Is it a long one? Is there many parts?
Yeah.
Okay, let's go for it then. So, what do we have for the first part then?
Define simple harmonic motion.
Okay, well, we can skip that then. Because
One
that's
end-
just in your notes.
Yeah. One end of a thin rectangular metal strip is firmly clamped to the end of a table so that the rest of the strip extends beyond the table and is able to vibrate with simple harmonic motion in a vertical direction. Consider the metal strip to be horizontal when it is
Equilibrium.
position. The free end of the material strip is pulled down 6.5 millimeters and released. The strip vibrates with frequency of 15 Hz. Determine the time period.
Okay, so what you do is you pull the metal strip down a little bit and release, and it vibrates. And is this A part 2?
It's It's only like part one. Yeah, B part one. Sorry.
B part one.
Yes.
So that's easy because the formula is time equals 1 over f, which equals 1 over 15 seconds, whatever that is on the calculator.
Determine the maximum acceleration.
Now, the maximum acceleration, we had a formula for that as well. A max equals, do you remember the A omega squared, and omega is 2 pi over t squared. So it's equal to the amplitude by 4 pi squared over what we just got a moment ago, t squared. So that's equal to 6.5 times 10 to the minus 3 times 4 times pi squared over 1 over 15, because that was the time squared.
Yeah.
So this gives us it in meters per second squared. We may need this answer now for the next part. So if we can calculate this. No, well that's okay, because I want to check that our answers are matching up with the mark scheme. So you can tell me if it's right. 6.5 times 10 to the power of minus 3 times 4 times pi squared over 1 over 15 squared. 57? 57.74, yeah.
Says plus or minus.
Yeah. That's for if the student makes an error, like an acceptable range.
Okay.
Yeah. Okay, what's the next part then? Well that's just A omega. So actually, if I just go back to what I typed in and delete my squares, so delete that square and the 4, it becomes a 2. That's all, isn't it?
Yeah.
So that will be 61.3 centimeters per second, or if you want it in meters, 0.613 meters per second. All fine and dandy. Part 4, Iyad?
Which point will the vibration occur?
Where does the maximum occur? Yeah, where is it?
Maximum speed is in equilibrium, right?
Yeah.
And
When
acceleration is an amplitude.
at the in this story here, it's at the horizontal for the maximum speed. Is it asking for the maximum acceleration location as well?
No.
Okay. But you're right, at the amplitude. Yeah.
Determine the time taken for the free end of the metal strip to move from a position 4 millimeters above equilibrium to a position 4 millimeters below equilibrium.
Now, that one's a bit tricky, all right. So, the full amplitude is 6.5 millimeters to minus 6.5 millimeters. And it's going from 4 to minus 4. Now, what's not clear here, for example, there's actually a couple of ways you can get from 4 to minus 4, which they weren't clear about here. Let me just get my colour here. So one way is that the metal strip could be on its way up. So then it has to go up and come back down to 4, minus 4. But the second possibility, which is what I think they mean, is that it's already on its way down. So it has to go from 4 to minus 4 on its way down. You don't know which, but given the context of the story, it's probably this. But if a student did it the other way, I would recommend that they still get the full marks, because there was nothing in the question that made you choose that over the other one. So anyways, how can we do this? Well, what we could do is we could work out the time it takes to go to 4. Then we could work out the time it takes to go to minus 4 and subtract. Do we need cos or sine here? Well, we're starting in the middle, so we need sine for this one. So we have the formula x equals a sine omega t. So here, that x is 0.004 equals 0.0065 sine, and we have the omega, it's 2 pi over t, which we can work out, times t. So can we actually just work, did we have to work out the omega yet? not directly,
Yeah.
not by itself. So that's 2 pi over t.
Yeah.
So that's 30 pi. So I'll leave it as 30 pi. So we basically have these two equations to solve. What am I doing? Sorry. What did I say? 30 pi t. That's to get to, let's call it U for upper and L for lower. So that's to get to the upper location, and then to get to the lower location, the only difference is you have to solve this. Now, if you think about this for a moment, sorry, I wrote that in wrong. It's not that, that's right, sorry. If you think about this for a moment and think back to your math class, how many answers should you have for this equation? How many answers does sine have? 2 answers. Do you remember how to get the second answer for sine? It's pi minus the first answer. And how many will this have? 2. Yeah. Now, if you have 2 answers and I want it on its way down, do you think I use the first or the second answer? Or the bigger or the smaller answer? No, bigger. Because the smaller answer is the one where it's on its way up, because that's the sooner answer. If it starts here, the smaller answer will represent the time to get here. The second answer will represent the time to get here on the way back down. So we need the bigger answer here. So I'll write B for bigger. Now, here, do we use the smaller answer or the bigger answer in the 2 answers? What do you think? So starting at the middle, on its way down, you have 2 answers for time. What do you want to use, the smaller or the bigger answer? The smaller one, because that's the one that happens first. Because if you use the bigger answer, then what you're doing is you're getting the time for it to go all the way back down and then up to -4. So you need the sooner time. So let's get the answers here on the calculator. It is 0.004 over 0.0065, and then that's sine inverse, and then that's, after you get the sine inverse, you have to divide by 30 pi. 0.403 seconds. Now we should see what the second answer is. So the second answer you do, where's my close bracket?
Shouldn't be in range.
Very good. My answer is totally wrong. 7 milliseconds. Right, now the second answer you have to, what is it, pi minus the first answer. But you do that before you divide by 30 pi. So it will be pi minus that. Because remember the IESF steps, so the extra answer happens before you simplify. So the second answer is a bigger 0.0263. So we said we want to take the bigger answer. We repeat, the only difference this time is a minus. So if I just go to the calculator and change that to a minus, the first answer is a negative, which we'll then have to fix. And then the second answer was with the pi in it. Do you remember the steps, IESF? No?
I remember the steps, but I won't be able to do this.
Oh, okay. I said I want the smaller answer here, don't I? Yeah, the second one, 0.04. I think I did that right. So if I add 0.04 to 0.0263, what answer's in the marking scheme? 0.0663. What do they have in the marking scheme?
Time taken
Yeah.
equals T1 minus T2.
Yeah.
7.33 to the 10 minus 3 minus 7.33 to the
Yeah, final answer.
1.41.
Okay, I think I have the wrong second answer for the other one. Come on. No, it's gone.
They used 0.007.
I think I have the wrong one here for the second one. Yeah? Do I have the right one for the first one?
No.
They used 1 minus 7.03 and 1 plus.
Ah. No, I understand what they did. So when I said I thought it was on the way down, because of the numbers they used, I can see that they did it as if it was on its way up and then back down.
Okay, so it's the same method, but...
It's the same method, but instead of taking the bigger answer here, they took the smaller answer because they did it on the way up to 4 and then back down to minus 4.
Which will give me different answers, but...
It'll give you a different answer, yeah. It will give you a bigger answer because more time has passed now to get from here down here. What would you say their answer was? 0.07 or something like that. The final answer.
1.41 to the 10 minus 27.
That's a smaller answer. Anyway, they did it the same way I did, but it sounds like they're looking at it from the top down. Okay, so that's a very bad question because it's not clear what the times are here. So I would say, to be fair, in each of these cases you have two different answers, but they didn't make it clear which of the two to choose. So if this was a real exam, I was correcting for you. No matter whether you chose the bigger or the smaller answer in each case, I'd still recommend getting full marks for it because there's nothing in the question to make you choose which of the two. Unless there's something in the question that says it's on its way down or it's on its way up.
Maybe at the beginning.
No, I don't think at the beginning. Well,
The free end of method.
no, there's nothing, no, I think that's an unfair question. Right, what's next then?
A few grains of sand are placed on the free end of the strip.
Yeah, so they put some sand here.
Determine the maximum amplitude of vibration if the grains of sand are stayed throughout its motion.
Yeah, so what's happening here, you put some sand on the metal rod. If you pull the metal rod down too much and release, the sand will fly off the rod. But if you put it down a small amount, you can keep the sand on the rod as it vibrates. So the question they want to know is how far down do they have to pull it so that it stays on it? So how on earth could you find that? So what's going to happen if you picture it here? When the rod, for example, is on the way down and the sand is on top of it as well, the sand is on its way down as well.
Yeah.
And the reason it falls off is if the metal rod's acceleration is bigger than 9.81, because what it means is the rod is falling faster than gravity. So it's almost like the sand is left hanging as the rod falls down, you know. So like if the rod moves slowly, then the sand stays on it. But if the sand falls faster than the rod could fall under gravity, then it loses its contact with the rod. So the question, although it's difficult, is really asking you, you want the maximum acceleration to be 9.81. And the formula is A omega squared equals 9.81. So really, the answer is just 9.81 divided by omega squared, which is 9.81 divided by 2 pi over t. Oh no, we worked out the omega earlier, didn't we?
Yeah.
So it's whatever omega we got previously. Did we write it down? Did you write it down or? No. Okay, that's okay. I think I wrote it down, didn't I? Oh yeah, it was 30 pi.
Yeah.
So it's if you just take out your calculators and do 9.81 divided by 30 pi squared, like this.
What is that 35 square?
That's omega.
Yeah.
That's what we worked out previously. 1.1 times. So in other words, 1.1 millimeter. Okay. Is there more to it?
The appearing parts increase slightly at what point in the motion will the time lose contact with the metal plate?
If the amplitude is what?
Determine in part 6, this one,
Yeah.
is increased slightly. At what point in the motion will the time lose contact with the metal
So
plate?
in other words, the question is, when would the sand fall off?
So when it's bigger than...
Yeah, but at what point in the motion will that be?
Okay. Do I use omega times? Do I use that? X equals...
No, it's not as difficult as that. I'm willing to bet this is a 1 mark question.
It's a 2 mark.
If you think about my explanation here, it would fall off when the rod falls faster than the gravity. So the question you need to ask yourself is, when would the rod be accelerating the most? Yeah, at what point in the journey is the acceleration the greatest? Yeah, the horizontal. Yeah.
It's just like this one.
So what's going to happen is here, the acceleration for the rod is greatest at the beginning. So at the very beginning, this is when you have the A max, which will be bigger than 9.81. So at the very beginning, the rod is accelerating downward faster than the sand is from gravity. So this is when the contact is lost, right at the beginning. But of course, you have to pull the rod down for that to happen. So if you're pulling the rod down, if I do this in slow motion, the rod is pulled down. As it's moving up, the sand is still in contact with the rod because it's pushed against the rod. So here, I think, it is when it will lose contact. But you think, well, no, it won't, because the rod is on the way up, so it can't exactly fall through it. You get what I'm saying? So
when it's coming down the second time.
yeah, when it's coming down for the second time, definitely. But I do wonder if it will fall off when it's at the top. So the two answers I have in my head is when it's at the top or when it's on its way back down in the middle.
I think on the top.
Yeah.
The top does make sense, yeah. Whew, I don't know.
The answer is
I would go with the middle if I have to pick one.
No, the answer is in words.
Yeah.
The sand will lose contact as the ship starts to move downwards from its highest point.
Ah, so they went with the top then. When it starts moving downwards from its highest point. I suppose that makes sense because you're flicking the sand off of it. But please note, if the rod was pulled upwards at the beginning and released, then it would definitely fall off when it gets to the middle. No, you seem confused by that. It depends on which way you pull the rod. So for example, if the rod sticks out here like this, and you put the sand here and you pull it up and let go, the sand will stay on it until it gets to the middle. And then what will happen is this will fall faster than the sand will, so the sand will lose contact. If you are pulling it down and have the sand on it, it will rise. And the reason it doesn't lose contact at the middle is because the acceleration is upward, so the sand actually can't fall off. So I guess when it reaches the top, comes back down, that's when it loses contact, yeah. This is kind of a tricky one to picture. You really have to have a good imagination. Okay, what's the next part then?
Get a graph of displacement y-axis against time.
For the metal strip?
by the end of the strip to illustrate the effect of air damping on the vibration.
Yeah, this is the damped motion then. Now I see that the graph is kind of upside down because if you're pulling the strip down, then at the beginning the displacement is negative.
Yes.
But that's easily fixed if you just call down positive and upward negative. So both is fine for the picture, it doesn't matter. So I'll draw mine upside down because I prefer to have it this way. So, and also I see that the graph starts at 0, which it doesn't here, because if you pull it down at the beginning, you start off with a negative displacement. In their picture I can see that they have it starting at 0, which isn't what's happening in the story. So for me, I would draw it like this. It starts negative, then it increases to 0, and then it goes positive. But in real life, it doesn't go as positive as it was negative because the air is slowing it down. So for example, if this is 6 millimeters, then maybe it only makes it to 5 on the way up because the air slowed it down. So the graph would be getting shorter each time until it's no more displacing.
This is the last part.
Yeah.
Version 4, 13, 14, B6.
Okay, before
That's the fields one, yeah.
before we go on, just to clarify
Yeah.
the difference between A omega, sin omega t, and A cos omega t.
Yeah, when to use which is which. Okay, so the difference is when you have simple harmonic motion, if the motion in the story begins at the center, that's use x equals A sin omega t. However, if the motion is beginning at the end, that's when you want to use A cos omega t. So the difference is between sin and cos is whether you're at the middle or the end. Now the way I remember it is sin 0 is 0. So the one that you want to be 0 at 0 time needs to be the sine, because you want your answer to be 0 at the beginning. Because remember, this is the origin and this is positive and this is negative.
Okay.
So it has to be sine because it has to be 0 at the beginning when t is 0. So then the other one must be the cos. Are we doing a fields one?
Yes.
Yeah? Okay, fields it is then.
Yes.
What year and version then?
Version 4, 13, 14, B6.
Okay. First part, A1? Yeah.
Define electric field strength.
Okay, so this is a definition from your notes, okay.
Draw and label.
That will be shown. Yeah, we have that.
Draw and label which diagram?
The electric field line for a positive point charge.
Yeah, that's okay, isn't it?
For a positive point charge.
Okay. The equipotential stuff is something people forget. So part 1 and part 2. The electric field lines for a positive charge look like this. Roughly, I'm not doing a beautiful job, but you get the idea. They extend outwards. And the equipotential lines, does anyone remember? They're circles around it. They're the equipotential lines. They are the lines at which the potential energy is the same for the different levels. In other words, they're like energy levels around your atom. You've done shells and all of that in chemistry. So that's part 1 and 2 of that one. So what's next then?
The electric field strength at a distance of 5 centimeters from a point charge of +4 microcoulombs located in a vacuum.
Right, so the formula for electric field strength here is your KQ over R squared. If you check your formula book, I think the K is 8.99 times 10 to the 9. The Q is 4 times 10 to the minus 6. And 5 centimeters is 0.05 squared. It's in there somewhere. It might be in a newer version of the exam.
Okay.
Yeah. No, it's big K, not small K.
Yeah,
That looks like it.
10, 8 or 10, 9? Yeah, 10, 9.
Okay. So if you hit that in, you get the answer. I won't bother doing that because it's just a calculator. That's the formula. What's the next part?
On B 2.3 charges A and B of 9 microcoulomb and minus 2 microcoulomb.
Okay, 9 microcoulombs and minus 2 micro.
10 centimeters apart in a vacuum.
10 centimeters apart in a vacuum, okay?
Determine the position of a point P on a line XY passing through the charges, where the resultant electrical force on an ionized air molecule will be here.
Right, so I'm going to take the 9 as the origin. So, is it a positive charge, it said, or? No, the charge where you want it to be. Well, I guess it doesn't matter. So, let's imagine you had a small positive charge, and let's put it here, for example. What forces will it experience? Push to the right and...
Push to the right.
Yeah, so it could not possibly be balanced here, because there's no force acting to the left. Because it's being pushed to the right and pulled to the right. Because this is a negative and this is a positive. So then we might have to consider putting it here, left of the origin. We'll put the origin at the 9. It'll be pulled to the right. It'll be pushed to the left from the 9, but it'll be pulled to the right to the minus 2. So it could be here. And what about if it's over here? Well, it will be pulled to the left for the minus 9 and pushed to the right from this. So we are going to have two answers here. And interestingly, one of the answers will be a negative and one of the answers will be bigger than 10 centimeters. And we should not get an answer between 0 and 10, because we just see in the diagram that it couldn't possibly be balanced. So let's consider the answer on the left first, as our first possibility. So let's call this distance here x. So what is the force from the 9? That would be K, Q1, Q2, and let me call the small, you know what? I'm going to call this small charge here Q, small q. So it'll be K, Q1Q over R, which in this case is x squared, and that should equal K, Q2Q over x plus 10 centimeters squared, because the distance from here to this one is x plus 10. So we have to solve this, but what's nice is that the k's and the q's cancel. So you're actually just trying to solve q1 x plus 0.1 squared equals q2 x squared. Actually, if I divide that, I'll have x squared here, and then if I divide by q1, I'll have q1 here, and that's actually not too bad to solve because you can square root everything. So you get x plus 0.1 over x equals the square root of q2 over q1. I'm going to wait till the very end to use my calculator. So that would be x plus 0.1 equals x times the root of q2 over q1. So that means x minus x root q2 over q1. No, that's ugly. I'll take this x to the right, and then I can factor it out. Root q2 over q1 minus 1. So finally, the x will be 0.1 over root q2 over q1 minus 1. And that is a positive number probably, but it's to the left.
9 over minus 2?
Yes. Oh, and I shouldn't have the minus in there because I already have the minus because I have the direction. So it'll just be 0.1 over root minus 1. Q2 is on the right. That's the 2, isn't it?
The one on the right
is
the minus 2.
Yeah. Oh yeah, I guess I put the minus in for me. I wasn't expecting that though. 18.9 centimeters. Well, I don't know now. There's two answers here because you can have a plus or a minus. So let me just see what happens if I change this to a minus. Yeah, I get a minus. So I get an 18 or a 6. So 18 centimeters or 6 centimeters, depending if you take a plus or a minus. Now let's see what happens if we're looking, if this is over here, then the difference in the formula would be, let's see, the distance from here to here is 10 plus. I think this, the only difference is the 0.1 would be on this one, wouldn't it? Let's form the equation.
This is the answer.
Yes, I'll get to that now in a second. We can check it. I'm just trying to get the second answer here. So, okay, let's look at it from over here. This would be all the way from here to here. So that distance is, yeah, I'm sorry, I'm calling x now the distance from here to here. I'll call it x. So that will be k q1q over 0.1 plus x squared, and then the distance from here to here is just x. Yeah, so the only difference in the formula is these two are swapped, which affects only this one will be over this one here. So if I just swap them, we'll take the plus answer first. I get, again, 9 centimeters. And then the other one is, if I take the minus answer, I get 3 centimeters. So in my picture I have 4 answers. I'm not too happy about that. So there's the 9 microcoulombs, there's the 2 microcoulombs. So firstly, the first answer I had, we could have 18 or 6 centimeters to the left. And the second one here is 3 centimeters or 6 centimeters. Now I'm rounding off, it was something like 5.9. So what answers did you have in the end?
They have 8.92 centimeters for the forces on the M1 to be equal, and opposite x will be to the right of B, which is so x equals 8.92.
Okay, so that's that answer there, I think, that I rounded off badly. And the other possibility? Or they just have one? So how do you know which answer to take, because we have 4 answers here? The only way to choose which answer to take is you would have to take your answers and put it back into this formula here to see which ones actually work. It's a very hard question, and I hope there was a lot of marks for it. Not worth it. It's too much work here for 4. This really should have been 6. Quite an involved question. And questions I've seen that were like this in other years, I think probably were 6 marks. So this is kind of what Ian was saying earlier. Like, why would you choose to do the fields question in section B? It's extremely difficult. There's more to this, isn't there? Yeah. So what's the next one?
Magnitude of the force at P due to just one of the point charges if the air molecule has lost 2 electrons.
So what you have is, which one do you keep, A or B? Well, read it again. Due to...
determine the magnitude of the force at P due to just one
B.
The point.
At P.
The P from the previous one.
Yes.
Due to...
Just one of
there are two electrons.
So you have A, you have B, and if it lost 2 electrons, it has a charge of +2, because it lost 2 electrons. Now, it says, what's the force experienced due to one of these? And you might say, well, which one? But if you remember, the whole reason you did the previous question was to find a location where the forces are equal. So this one is the positive and this is the negative. So the B will be pulling it to the left and the A will be pushing it to the right. But you know that these should be equal because that's what you just did previously. So it didn't have to say which one, because whichever one you go for, you'll get the same answer. So we might as well just go with the one nearest to it. So the formula, do you remember, it's K, Q2, Q over R squared. We know the K, it's a constant. The Q2 here, I think this is minus 2 microcoulomb, so this will be 2 micro. And what's the small q here? Plus 2, so it'll be 2e, because this is 2 electrons. And then the distance, we worked it out as something like 8 centimeters or something. Whatever you got on your calculator. So I'm not going to do that because it's just putting the 3 numbers into the formula, so that's all fine. The next part?
Define 2 marks, then 2 marks for sketch and 2 marks for distance.
Sketch what?
The magnitude field lines perpendicular to a long straight current carrying wire.
So this is the current is going to the right, and then this is the right hand grip rule. So it means the fields are going around it this way. So I'd have to draw the lines in like this. Okay, what's the next one?
5 multiplied to the 10 minus 2 meters length of a conductor carrying current of 3 ampere is inclined at an angle of 30 degrees to a magnetic field. Determine the magnetic flux density if the conductor experiences a flow of 3.56 to the power of 10 minus 2. 3.56 to the power of 10 minus 2.
That's the force?
Yes.
So this is the formula F equals Bill sine theta for this one. Yeah, the other one was cos. The B, so what are we looking for? We know the F, we know the I and the L and the theta. Are we looking for the B? Density. Yeah, so B equals F over IL sine theta, which will be 3.56 times 10 to the minus 3 over 3 times 5 times 10 to the minus 2 times sine 30. And we don't need to bother typing that in, but that's the answer there.
Let's do 8.
In this year?
Yeah, let's do it.
Okay.
Yeah. The plane of a rectangular coil having 100 turns of wire and carrying a current of 1.3 amps is parallel to a uniform magnetic field of strength 2.6 times 10 to the minus 3 Tesla.
Say that last strength then?
2.6 10 to the minus 3.
So millitested then. So the field is, again, like we've seen before, running across this way. Yeah.
The torque on the coil is 4.3 10 to the minus
4. 4.3 times 10 to the minus 4 Newton meters.
Determine the cross-sectional area.
Okay, so this formula is torque equals IBAN. So A equals torque over IBN. So that is 4.3 times 10 to the minus 4 over 1.3 times 0.0026 times 100.
Determine the magnetic flux linked with each time. This is
linked, you say. So That's the flux equals
BA
BA. Is it at an angle?
35.
Cos 35. Right, so the B is 0.0026. The A, we just worked it out previously. It's 4.3 times 10 to the minus 4 over 1.3 times 0.0026 times 100. And the cos theta is cos 35. Again, you just put that in on the calculator.
So one more field.
Yep.
Question?
Yes, yeah. Same year?
I have to search.
It's not difficult once you know what formula to use, but that's the thing, knowing what formula to use.
And in the long, which questions do you prefer to use?
I personally like the electricity and I like the mechanics
For what? For what?
for section B, and I like the materials and I like the atoms. I'm not too keen on the fields, and I don't like the waves too much, but they're all right.
Atoms, mechanics,
Materials.
materials, and...
Yeah, I don't.
In that order.
Yeah.
Last thing is fields.
Last thing should be
Never
fields.
Never. Unless I have...
I like the fields question when it's about gravitational fields. Kepler's second law.
Yeah, that was really good, actually.
Yeah.
But then they combine it with mechanics anyway. It's not completely...
Yeah, it's not completely fields, it's half and half.
They'll ask you about the mass and then all of a sudden...
Or density or something, yeah.
That one was really good.
Yeah, no, that was okay. It's the electric and magnetic fields that are difficult. Yeah, it's probably the hardest part.
Ever.
There is the gravitational field question.
In section A?
Section B.
But I think we did one. Is this about the planets?
Is there more here?
Moon, Earth.
Moon.
It's the only difference is we did Mars and the moon of Mars, and this one looks like the Earth and the moon of the Earth. And it even says at the end there, use Kepler's law to determine the mass, is it? Determine the radius. The one the one I'm talking about. We did this one. Did we do it twice? Okay, yeah. So I'm not going to do it 3 times.
Okay,
Okay, this is.
Section A or B? Fields?
Yes, B3, the beginning of it was here. No, then the second part.
Yeah?
B.
Oh yeah, that's a fields one for sure. Yeah. Okay. So what do you have here? You have a north on the left, is it? Yeah, north is south, and then you have the rectangle through it here. Okay, and then read the story. What info do they give you?
A coil consisting of
Yeah.
a single turn of thick copper wire of cross-sectional area 4.5 multiplied 10 to the minus 4 meters square is placed in a uniform magnetic field of flux density 0.05 Kelvin. The coil is free to rotate about the axle. Determine the magnetic flux length with the coil when the normal to the plane of the coil makes an angle of 25.
Okay, so that's the formula BA cos theta. So that'll be 0.05 times 4.5 times 10 to the minus 4 times cos, I'm sorry, what you said the angle was?
25.
25. And that's it. You just hit that in the calculator.
The coil is connected across a resistor. The coil is then made to rotate in a clockwise direction, as viewed from the end AD.
Yeah.
When the rotating coil is momentarily in the position shown, state the direction of current in the coil as
Okay,
viewed from above.
great. So they want to know what direction is the current. So that is the right-hand rule, I hope. force, field, current. So it's going up. So I'm going to put from my point of view, this is going up, and then the current is going to the right. The field's going to the right. So for me, the current is going into my screen. So when you use your right hand here, the current is going from A to B, which means it's going from A to B to C to D. So the current is going this way around. I hope. Is that the answer? If I did that right.
Fleming's right hand rule, the current will flow in the direction A, B, C, D. Determine the maximum flux linkage with the coil.
Right, well that's not one we have done, but I hope you can work it out. They want to know what's the maximum here, and you use this formula to figure it out. Can you change the B? No, because that's just a property of the magnet. Can you change the A? No, that's just a property of the piece of metal you're using. The angle you can certainly change. So at what angle will you make cos theta a maximum? In other words, what is the biggest cos theta can be? 1. And at what angle will that occur?
90.
No, 0. You got it the other way. So just simply multiply B by A. So in other words, delete the cos 25. And you have the answer. So that's all fine as well. The next part?
The resistor is then replaced by a battery and a current of 1.5 ampere.
Okay.
It goes through the coil in the direction A, B, C, D.
Okay.
Determine the initial direction of rotation of the coil when viewed from end A, B.
Okay, so what's happening now is I think they've just they've changed it from a generator to a motor, and they're running a current through it so that it starts to rotate by itself instead of you rotating it to make the current. So this one is the left-hand rule. So the magnetic field is still going to the right. The current is now, for me, going in. So the force is going down here, and likewise the force will be going up here. So it'll rotate anti-clockwise. So this is using the left-hand rule here. Okay. 1 mark?
Yes.
Yeah.
The maximum torque on the coil when a current of 1.5 is going through.
Now here there's only one wire, so the N is 1, so it's just IBA. What did you say the current was, sorry?
1.5.
1.5. And actually you have the answer BA from the previous one. Yeah. So I'll just write down here maximum flux, because that answer you have, that's the previous answer here. So you just multiply that by 1.5 and you've got it.
What's the last question here?
That was the end of the question?
There is one more.
Which position?
The torque will be 0.
At which position will the torque be 0?
Yes.
So if you look at the formula, torque equals IBAN, or if you want, that's NBAI. Now this part here is what changes if you have a different angle. This one, if it's at an angle, is NBA cos theta. Because the formula is a bit like this, phi I. So it's like this part of the formula has the angle in it when you have to consider an angle. So if you want the torque to be maximum, again you want the cos, just like before, you want the cos to be maximum. And I already said when that happens, when that's 0. Now you have to be careful here. This is the angle between the normal and the field. So for example, if I draw the field this way, and I draw my board this way, the normal is this way, the theta is the angle here. So when the theta is 0, then it means that it must be lying this way. So the plane must be vertical then. So in other words, the maximum torque happens between the north and the south when the plane is in the vertical position. Is this like a 1 Mark 1 or something?
2, I think. Yeah, 1 more. One more fields question.
Yeah, we can do a section A1 or something, I think.
B3, version 4, same year.
I don't think there's time to do a B1. There's no A1s in that?
No.
No. Well, maybe we should think about for next week. So look, next week's the last week.
Yes.
We have classes every day?
Yes.
Monday, Tuesday, Wednesday, Thursday, Friday, yeah. So if you think about it, what do we have? 6 maths and 6 physics. So that's 12 hours. That's still a highly significant number of hours. Next week, it's the last week. I need to be doing what you want to do. I can't just be continuing doing questions randomly because we need to be focused on what your actual needs are. So all I'm going to do in the 12 hours next week is whatever questions you can't do. This, of course, requires you spending some time to compile a list of questions to do in class. So what would make me happy is if on Monday I all see in your notebook a piece of paper broken in two, physics on the left, maths on the right, and I would like to see a list of questions, 13, 14, version 2, A6, etc. If you all come to class with a list of questions to do, then we have our schedule for next week of what to do. And as long as everybody doesn't have too many questions, then we could possibly get through all the questions. But I'm sure some of you might even have the same questions. If you don't come to class with this, it just means we're spending time for you looking at questions you want to do. Or what I feel is worse is I just start randomly doing exam questions, which I could do, but I really want to make the last week very focused on your needs. Do you understand what I'm saying?
Yeah.
So please take the time. It'll probably take you 1 or 2 hours because you'll have to very thoroughly read the past exams to figure out what you need to see. But spend the 1 or 2 hours over the weekend compiling this list and come to class on Monday or don't. That's your choice, I suppose. But I think we'll wrap it up there. The best thing you can do now is head off and go to the library and start compiling a list of questions. Whoa!
Did you push out weights in the notes board?
I didn't, because to be honest, I wasn't feeling the engineering love this week. Do you know what I mean? Now, I've already given them to Musharif because he came by the office. So if you want to come by the office, you can.
Right
Your
now?
grades so far that you've gotten.
Right now?
No, I have another class right now. But look, if you want to email me, I can reply in the email because I've got so much to do. I don't know if I'll have time even to print them out and put them on the notice board. I know it sounds like that's a quick thing to do, but it's not because I have to delete your name so that it's private and I have to put in your student number.
You can, it's just the lab report and...
Yeah, but it's the maths and the physics, isn't it?
Yeah.
You can send us together, it's fine, we are
No, I want to keep it private. It's not really right to give it to you like that. If you send me an email and put in the subject of the email, engineering September results, then I'll reply to it as a priority.
Alright.
I get a lot of emails, so I need to see this in the subject line so I know to reply to it first, okay? Only send it twice if I don't reply. No, unplug it. Right, possibly see you Monday.
Charging?
Yeah, it's a battery powered projector.